Let's talk about estimating the average of some probability distribution that's generating our data and talk about how we can come up with a confidence interval for that quantity. Because very often that's really all we're interested in really studying about a probability distribution. A lot of times we don't really care what distribution's making our data. We would just like to know what's a typical value that we might observe. What's the average or expected value? So, a lot of times in analytics, we're really only interested in estimating the probability distribution's average. We don't really care if the PMF of whatever distribution's making the data that is giving us the number of items that people have in a cart, if it's Poisson, if it's negative binomial. We don't really care if the length of time that someone spends on a website is normal, log normal, Weibull. We would just like to get a feel over what the average value is. And to motivate this, let's take as an example what's going on right now with the 2020 census. So you might have filled out your census form, your parents might have filled it out, but by law, every household has to fill out the census form that lists how many people live in the house and some additional information. Looking back at the 2010 census results, we can look at the distribution of the response rates for all of the block groups across the United States. Now, a block group is something like a few different zip codes typically. It's a fairly large area. And so we see that there's some distribution that's skewed off towards the left here. But if we were more interested in just quantifying, well, on average, what is the response rate going to be for any particular block group, we don't really care what this PDF is. We just want to know what the overall average is. If we had an idea on what that average was, we could compare different states, different zip codes to the overall average and see if they're better or worse. And so in this case, we don't really care what that probability distribution is. We just want that average. So heading on over actually to the 2020 Census website, they have a nice map that is letting us know how many people have responded so far to the census forms, either online or they've mailed it back. I know I personally just filled out my census information online. So we have this 33.1% national response rate, and maybe we'd like to know, well, is Tennessee doing better than this average? Is it doing worse than this average? Maybe there is some PDF that's spitting out values for what the overall response rate is in a particular state or a particular zip code, but we don't really care what that PDF is. We just want some information about the average. So here's Tennessee. The average response rate across the country is 33.1%. Tennessee, a little bit higher. Maybe we'd like to make some sort of statement regarding the statistical significance of this difference, if it looks like Tennessee is doing a little bit better than the rest of the nation. Or maybe we'd want to dive in even a little bit deeper and go on a county by county basis and maybe compare counties to each other. So these are color-coded by the response rates. Here we have Grundy County with a pretty small response rate so far, about 15%. Knox County looks like it's doing quite a bit better, more than double than that at 34.7%. So are there statistically significant differences in, say, the average response rates that we see on a county-by-county basis? We don't really care what the PDF is that is responsible for generating these values. We just want to be comparing averages. And so that's going to be our overall goal of Unit 11 is talking about, well, if the average is really the only thing that we care about, these probability distributions, how can we go about estimating it from data? How can we come up with a confidence interval? How can we compare different groups to each other? And we can answer some pretty significant and important questions once we have a handle on how we implement this procedure. So I think the most important thing, at least in business analytics, is when we start actually talking about comparing groups averages. So is there a statistically significant difference, example, in response rates for neighborhoods that have predominantly renters versus predominantly homeowners? Is there a difference in response rates based on where people are living, mostly urban communities versus suburban versus rural? Is there a difference in response rates on average if we look at the ethnic makeup of different block groups here? And just looking at some of the raw data from the 2010 census, it looks like that there might be differences in different block groups. If we look at the distribution of response rates across block groups and compare that with block groups that mostly own their houses versus mostly rent their houses, It looks like there's a pretty big difference looking at the average. We got an 82% versus a 72%. But how do we go and make a comment on whether or not this is statistically significant? If this sort of difference can be explained just by random chance from just the act of going and collecting data, or what? How can we make this analysis? If we go and compare the response rates, the average response rates, for block groups that are mostly urban versus suburban versus rural, well, we see a small variation here. Are these variations statistically significant? Or does it look like that this variation, which really isn't all that big, could be readily explained just by random chance that we would expect to occur whenever we go and collect random samples of data? And same thing for racial breakdowns. We do see a relatively large variation in response rates as we go through block groups where the majority race is Hispanic, white, black, Asian, etc. Are these differences statistically significant? Or is this variation just naturally explainable just by the act of collecting data? We don't expect them to match up exactly. We expect some variation. What can we say about this? So that's our overall goal of Unit 11. We don't particularly care what the PDF or PMF that's responsible for making our data is. We just are interested in estimating the average of that distribution. And if you remember, our universal symbol for the average of some PMF or PDF, the expected value, is this Greek letter mu. So mu is some parameter of any probability distribution that we can talk about. It might not be written in terms of mu. Basically, the normal distribution has that mu and sigma. That's the one where we're used to seeing mu. But the mu parameter is something that we can calculate for any distribution. We have a formula for the expected value of x. And so what if that's what we care about? What if we don't care about theta in general? What if we just want to estimate mu here? Now, the good news is that there's actually a remarkably easy and pretty flexible procedure for coming up with a best guess from you, along with a standard error, how far off we think our guess might be from the truth, and actually a confidence interval from you based on the data that we've collected. And it all hinges upon the most important result in all of statistics, called the central limit theorem. And there's a whole other video that actually dives into what the central limit theorem is all about, where it comes from, why it's useful. And so I'll refer you to that video to actually get a review on that. Instead, what I'd like to do is to just talk about the procedure for estimating mu. This is something that we do on a day-to-day basis in business analytics. And so how do we pull off this procedure? So this is something that's so common, so popular, that you learned about it in Stat 201. So this is more or less just a review. It's a refresher. So we've talked about optimal estimators. We've talked about bias, variance of estimators. So what should we measure from the data to estimate mu? Well, mu is the average of the data generating distribution. So logically, it makes sense to maybe calculate the sample average. We've collected some data, we have a whole bunch of x's. What if we just use the sample average, x bar, as our guess for mu? Is that a good idea? Is there something better that we can do? Well, it turns out that the sample average really is the best that we can do. Number one, the sample average is always going to be an unbiased estimator of mu. Sometimes the sample average we measure is a little bit above, sometimes it's a little bit below, but on average, we hit it right on the head. We like unbiased estimators, so that's a great property of the sample average here. So the sample average is always going to be an unbiased estimator. And we actually have a very simple formula that lets us know what the standard error of that estimator is. We don't expect x bar to match up exactly to mu. It might be a little bit above or a little bit below. But there's a formula that tells us the typical difference between the sample average and what mu is in reality, that standard error of x bar here. All we need to do is take the standard deviation of the values that we've measured in the sample. We'll abbreviate that as S. Divide that by the square root of the sample size, and that's going to be our formula for the standard error. So this is letting us know how far off we think our sample average might be from the truth. And we can see that as the sample size gets bigger and bigger and bigger, the standard error is going to get smaller and smaller and smaller. That's kind of the law of averages. It's not really a law of averages, but when we talk about something informally like the law of averages, with a large enough sample, what we measure for the sample average is going to be really, really close to what mu is. the expected value, the average value of whatever probability distribution is making our data here. And so that's the great news. We can estimate mu for a probability distribution just from the sample average, and we'll kind of be able to anticipate how far off that sample average might be from the truth. Get that standard error, and we can interpret it. So we measure a sample average x bar. We can interpret the standard error in a few different ways. We can say, the measured value of the sample average is likely to be off from mu by about a standard error or so. Or we can estimate mu to be the sample average, give or take a standard error or so. Or we could even say that the typical difference between mu and what we measure for the sample average, x bar, is a standard error or so. So let's see this in action. Actually, one of my favorite data sets that's built into Reg class is a data set that was inspired by a Kaggle competition. So you might have been a tourist in some big cities across the US or across the world, and you might have seen these bicycle kiosks where you can walk up, you can rent a bike, you can ride it across town, and it's a great way to see the city. This Kaggle competition focused in on the Capital Bike Share program in Washington, D.C. And you actually have seen some of these around campus, actually. It's kind of been supplanted almost by these little electric scooter things. But you still see you still see bikes as part of these programs all over the place. And so this data set provided the user with a whole bunch of different days and the daily demands for each one of those. And so we might like to pin down what we think is the average demand of whatever probability distribution is making this data, whatever distribution is responsible for churning out these numbers here. So let's actually bring this up into our studio here. We'll make sure library reg class is loaded up, and I'm going to load up the ex7.bike data set here. So in ex7.bike, we have a column for the daily demand, and so let's take a look at the values here. Let's just make a histogram of the daily demand. And we can see that it's actually pretty widely variable here. If we get a summary of the demand, we can talk about the properties of the data that we've collected. On average, from the data at least, the average daily demand is 4,800 bikes. And we always like to follow that up with a measure of how variable, kind of a give or take. If we ask for the standard deviation of the daily demand, we get a standard deviation of about 1760. Now, if you think back to Stat 201, how do we interpret the standard deviation? Well, this was the typical difference between the observed values in our data and the overall average. So typically the daily demands are about 4,800, give or take around 1760 or so. The standard deviation lets us know how variable the collected data values are away from the overall average. So some distribution, roughly symmetric, we could go through the zoo and maybe try to fit it to a distribution, but in this case, we don't really care what the distribution is. We just want to come up with a good guess for what the overall average value is for the daily demand. And we've already talked about, well, a good way to guess what the average value is of that probability generating distribution. Our best guess is just the sample average, the mean, that's that 4,800. And if we take the standard deviation of those data values, that 1760 here, and divide by the square root of the sample size, we can get the number of observations just by using the length vector, or length command, on the column of data values. We get a standard error of about 87. So what does this tell us? Well, the sample average was right at about 4,800. And so we think that the true average, the true value of mu of whatever distribution's making this data, is about 4,800, give or take maybe 87 bikes or so. We feel like we've nailed down what the value of mu is to around 87. And we'll talk about how we could come up with a confidence interval for mu here in a second here. But that's how we interpret that standard error. This guy right here is our standard error, that standard deviation over the square root of the sample size. The standard error in this case is around 87. The typical difference between the sample average that we've measured and mu is around 87 in this case. So that's how easy it really is to talk about the average of some probability distribution. We don't know what it is in this case, but we have a pretty well-defined procedure for talking about what we think the average might be, at least, give or take a certain amount. So the rest of these slides kind of go through and review what we just talked about right here. And so let's take this a step farther. So we have an idea for what the average demand is for these bikes. We have an idea of the give or take associated with that average as well. So can we do something similar as to what we did when we were estimating P, the probability of some event occurring, and when we were estimating theta, just a parameter of a probability distribution with the MLE? Can we come up with a confidence interval? Can we come up with a range of values for mu that are plausible based on the data that we've collected? And we can use basically the same reasoning as what we've employed before when we were coming up with a confidence interval for P and for theta here. This ties into the central limit theorem, where I have that other video. And here were some of the highlights from that video. Number one, if we go and actually collect data from a probability distribution and measure the value of the sample average, we're not going to get the same value every time. There's going to be some variation. Some samples are going to have a value of x bar that are a little bit above mu. Some samples are going to have an x bar that are a little bit below mu. But it turns out that the overall distribution of the possible sample averages that we might observe when we go and collect data is going to be approximately normal. Regardless of what that PDF is or what that PMF is, that's what the central limit theorem is telling us. So we can actually anticipate that, okay, sure, we might not measure mu exactly, but the possible values for the sample average that we might measure has a normal distribution, might be a little bit above, might be a little bit below mu, but the overall distribution of the possible sample averages we might see is centered upon mu with a predictable standard deviation with this normal curve here. And we know a lot about the normal curve at this point. We know that 95% of values that follow a normal distribution are within plus or minus 2 standard deviations at the peak. And we have a pretty good guess for what that standard deviation is. That's our standard error. That's the standard deviation of the data values we've collected divided by the square root of the sample size. So what if we do something very similar as to when we were estimating P, or estimating theta, and take our best guess, x bar in this case, and go plus or minus 2 standard errors? That was our procedure that got us a 95% confidence interval for P. It got us a 95% confidence interval for the MLE. So is that going to work here? Well, almost. It turns out that there's a little bit of a twist, a little bit of an extra complication that we need to take into account to make this analysis legit. So what is this extra complication? Well, x bar is our best guess for what mu is. We have a formula for the standard error, how far off we think x bar is from mu here. But there's something special about this formula for this standard error. Notice that the formula for the standard error involves calculating the standard deviation of the data values that we've collected in our sample. So in order to estimate how far off we think that our sample average might be from mu, number one, we have to estimate from the data the sample average, and number two, we have to estimate this additional quantity, the standard deviation. There's two things that we actually have to estimate from the data to actually figure out how good our guess for what mu is, and that's going to add in a little bit of extra randomness, a little bit of extra uncertainty into our procedure. The sample values that we collect are a little bit random, and so when we use that sample twice to do our inference, well, that's injecting a little bit of extra randomness in the procedure. That randomness wasn't involved when we were actually trying to come up with a confidence interval for P. When we came up with our best guess P hat, the fraction of trials where we saw our event of interest, the formula for the standard error used that value of P hat. We didn't actually have to estimate anything new when trying to guess how far off our value of P hat was away from P. And it was the same thing for the MLE. When we were trying to estimate theta for a probability distribution, we estimated theta hat. And it turns out that if you really dive deep into the math, the formula for the standard error just depended on the MLE itself. There wasn't something extra that we had to calculate from the data to complete the analysis. But when we're trying to make an inference on mu, there are two different things we have to estimate from the data: the sample average and the sample standard deviation, the standard deviation of the data values. And so we actually need to account for this extra randomness and uncertainty when we construct our confidence interval. We actually need to make that interval just a little bit wider to incorporate the extra randomness that's involved. And so, in this case, we can't just go plus or minus 2 standard errors. That 2 emerged from the normal distribution that was doing a good job of anticipating the distribution of possible values for the estimator we might see when we go and collect data. We need a new distribution. And it turns out that people have studied this problem, and one distribution that tends to do just the right job at incorporating that extra uncertainty, that second thing that we're having to measure from our random sample, this t-distribution is just the right distribution here to figure out the number of standard errors that we have to go from our sample average to actually come up with a confidence interval here. Plus or minus 2 isn't necessarily going to cut it. We probably have to go a little bit more than 2. The t-distribution is going to allow us to figure out how many standard errors we need to go from our sample average to come up with a confidence interval. So what is this t-distribution? Well, that t-distribution is the sampling distribution of the quantity x bar minus mu over our formula for the standard error. In other words, it is the probability distribution that lets us know the possible number of standard errors that our sample average is away from mu here. So the t-distribution actually has a parameter associated with it. It has a thickness associated with it. How much thicker is it compared to a normal distribution? And it has a name for this parameter. It's not theta. We call it the degrees of freedom. It's kind of a cryptically named distribution here, or cryptically named parameter. But it's pretty easy to figure out what just the right value is for this parameter based on the data that we've collected. It's always just one fewer than the number of observations in our data set. So, kind of to summarize, x bar, unbiased estimator of mu, might be a little bit above for a particular sample, might be a little bit below, but on average it gets it just right. So we'll estimate mu from x bar. We know it's not going to match up exactly to what mu is for that probability distribution. It's be off by a certain amount. The value of the standard error is our best guess for how far off x bar is from mu. And if we go a certain number of standard errors away, that's going to come up with a confidence interval for mu. Unfortunately, for 95% confidence, we can't just go plus or minus 2. There's an extra little bit of uncertainty involved because there's 2 things that we have to measure from the data to really capture this. This t-distribution models that extra uncertainty just right. So the normal distribution in this plot here has an outline given to us by the black curve. You'll notice that for smaller samples, let's say a t-distribution with 2 degrees of freedom, if our data only had 3 observations in it, notice how much wider it is. When the normal distribution's right at about plus or minus 2, well, the t-distribution here with 2 degrees of freedom is still quite a bit higher. To get to that point, we actually have to go a little bit farther out. And it just turns out that that t-distribution is just the right distribution to model that extra uncertainty. So what do we have to do? Well, just like when we were constructing confidence intervals for p, for the MLE, or for theta here based on the MLE, we referred to the normal distribution to figure out, well, how many standard errors do we have to go to get our desired level of confidence? Same sort of thing here. We just have to figure out under the t-curve here, how many standard errors do I need to go in order to have that area equal the level of confidence? If I want a 95% confidence interval, how much do I have to go from the peak in order to get the area equal to that 95% confidence? Now, the procedure is actually really quite easy. What we'll do is use the QT function in R. So it's always kind of fun, actually getting a confidence interval for an average in R, because who doesn't want to run the QT function? So if I wanted to get a 95% confidence interval for a particular example here, like with the bike demand, well, remember our best guess for what the average bike demand was for the Capital Bike Share program, it was 4,800. Feel like we've nailed that down to around plus or minus 87 bikes or so. Let's actually get our sample size. 410. If I want to get a 95% confidence interval for this, well, what I can do is take x bar, my best guess, and go plus or minus some number of standard errors. That's s over the square root of n. How do I get just the right number? Well, I'm going to plug in 1 minus alpha over 2 What's alpha? Well, I need to look back and say, well, what's my level of confidence? I want 95% confidence in this case. So alpha is 0.05 in this case. So 0.05 over 2. And then take my sample size and subtract 1 from it. So 409 here. So how many standard errors do I need to go? Well, plus or minus, well, just about 2 in this case. It turns out that for very large samples, it's still plus or minus 2. This t-distribution, that is just the right distribution to model that extra randomness and uncertainty that we have when estimating mu. That only comes into a factor when we have really small sample sizes here. So like if instead I only had 5 data points, you'll notice that if I had a t-distribution with 4 degrees of freedom, I'd actually have to go plus or minus about 2.78 degrees of freedom here, or 2.78 standard errors. Kind of a word salad going on. All right, but that's going to be our procedure. This is how easy it is. This is the power of the central limit theorem that lets us know, kind of really without a doubt, how far off our sample average is likely to be from mu here, as long as we meet a certain set of conditions based on the sample size here, as long as we have a large enough sample. All we have to do to get a confidence interval, measure our sample average, measure the standard deviation of those data values, divide by the square root of n to get the standard error, how far off we think that sample average might be, and then go plus or minus some number of standard errors from the t-distribution. Run QT, smile a little bit whenever we run that, and we've got our answer. So that's how easy it is, and that's the great news, because as business analytics practitioners, a lot of times we don't really care what that probability distribution is that's making our data. We just want the average. So x bar plus or minus some number of standard errors, QT gives us that number here. The only thing we have to make sure of is that the central limit theorem is in full effect. We need to make sure that we're dealing with a large enough sample, and in business analytics we usually are. So let's very explicitly kind of write down some good guidelines for when it's okay to implement this procedure, when we feel like we have a large enough sample for the central limit theorem to be in play. So whenever we make a confidence interval about the average, all of our conclusions are tied in to an assumption that the sample size is large enough for this procedure to be reliable. Now, it turns out that the key thing that lets us know whether or not that the procedure is reliable is the shape of the probability distribution that's making our data. Now, I just said we don't care what it is. We don't care if it's a Weibull, a Poisson, a negative binomial, but we do care about its shape, actually, because the number of data points that we need to pull off this sort of inference, it's tied into the shape of the distribution. Now, since we don't know what that probability distribution is, we're going to make a histogram of values, and we'll make our call based on the histogram. So if we make a histogram and it's roughly symmetric, then we really only need about 10 or more data points for this large enough sample size condition to be met and the central limit theorem to be in play. And if you run that central limit theorem applet, you can kind of see that in action. As long as you're dealing with samples of about sample size 10 or more, the distribution of the possible sample averages that you might observe look really well described by a normal distribution there. If we make a histogram and it's slightly skewed, then about 24 data points or more is large enough to trigger this central limit theorem and have this large enough sample size condition be in play. If you're dealing with a very skewed distribution, well, as long as you have at least 100 data points, you're probably good to go. That's usually good enough to trigger the central limit theorem. So was this analysis going to be correct here for the bike demand? If I take my mean of the observed data values and then go plus or minus some number of standard errors, degree of freedom 409, times the standard error here, is this really going to be a good 95% confidence interval between 4630 and 4970? Well, yes. The histogram of these data values, it's roughly symmetric. So as long as I had more than about 10 or so observations, I would actually be pretty comfortable using this confidence interval. It looks like the assumptions would actually be in play. And I have so many data points here, 410, that really regardless of what the shape of this distribution looked like, I would have been okay in implementing this procedure. So, what's my overall conclusion about the average daily demand for the Capital Bike Share program? Well, I think the average is right at about 4,800, give or take 87 or so. I'm 95% confident that the true average of whatever probability distribution's making this data is somewhere between 4,630 bikes and 4,970 bikes here. All right, so at this point, it's good enough to review kind of, well, what's the difference between, the standard error of the average, this 86, and the standard deviation of the data values themselves. This is always a point of confusion for people learning about confidence intervals and inference about the average the first, the second, and probably the third time through the procedure. So let's kind of write this down explicitly. So whenever we get the standard deviation of a set of data values, that's letting us know how variable those collected values are around the overall average. For the bike demands, we saw the average was right at about 4,800. The standard deviation is about 1,760. So looking at the distribution of the data values, it's peaking right at about 4,800. And typically, the actual values that we observe are, give or take 1,760 or so. So pretty large variability in the observed values for this daily demand. So that standard deviation is just tied into how variable the observed values are around the average. 1,760, a pretty large standard deviation. The standard error of the sample average is letting us know how accurately we think we've nailed down mu. So we're estimating mu by the sample average, this 4,800. We are aware that's not going to match up exactly to what mu is for the probability distribution making the data. It's probably off by a certain amount. The standard error is our best guess for how far off our sample average is from mu. So sure, yes, the daily demands can be really quite variable. Typically, they vary from the average by around 1,760 or so. But with this large of a sample, we feel like we've narrowed down mu here for this distribution pretty well. Our estimate of 4,800 for the value in mu here is likely off by only about 87 or so. So that's really what that main difference is. And if you just keep repeating that to yourself kind of again and again, it becomes kind of rote. So definitely recommend doing that so you're absolutely crystal clear on the difference between these two. All right, so let's go back to actually slide 39 here. That's where the conclusion about the bike demands kind of comes up with the average, the standard deviation, and the standard error. So really kind of writing down what the difference is between the standard deviation and that standard error is here. And let's also go back to slide 55 to talk about that census, kind of our motivating example, where we looked at the distribution of the census response rates from 2010. Let's actually load up the census. Where are you at, census? 8.2. There we go. EX2 census here. So looking at the response rates, we see a little bit of that left skew here. So we'd probably need maybe about 24 or so data points in order to make sure that our confidence interval procedure is coming up with a range of values that's going to be reliable. And in this case, well, how many data points do we have? How many block groups do we have information from? 3,500. So yes, we've met this large enough sample size condition. Didn't even matter what this distribution looked like. We have so many data points that this procedure for coming up with a confidence interval is going to be pretty much airtight here. So what can we do with this? We're assuming that there's some probability distribution that is generating these response rates for all of the block groups across the United States. What's our best guess for mu of that distribution, the overall average? Well, we can ask for the sample average, so about 80.2% overall. If we get just the standard deviation of the observed data values, that tells us something meaningful. The standard deviation is around 7.5. So we do see a bit of variability in the response rates from block group to block group. Typically, they're right at around 80, give or take 7.5 or so. They're pretty tightly clustered around the average, with some block groups really lagging behind and some really quite good block groups up here. So how nailed down do we feel like we have mu estimated with this average of 80.2? Well, let's get the standard error. So the SD over the number of data points that we have, the square root of the number of data points. We feel like we've nailed down the average to, well, let's get length. Yeah, that's not going to work. We feel like we've nailed down the average to around 0.13 percentage points. So with so many data points, this 80.18, that is pretty darn close to what mu of this probability distribution that's making these numbers. With this many data points, we feel like we've nailed down mu to within, give or take 0.13 or so. We can make that 95% confidence interval just by taking that average and then moving the appropriate number of standard errors, plus or minus. Not 2 in this case, but running QT, 1 minus 0.05 over 2 for 95% confidence. Remember, this is written in terms of alpha, so that 100 times 1 minus alpha percent confidence interval. Weird way of writing it, but that'll be clearer in a later unit. Alpha is 0.05 to get 95% confidence. Degrees of freedom, in this case, well, we had 3534 data points, so we'll put in 3533. That's going to be right around 2 with such a large sample. And multiply that by our standard error. So we're 95% confident that the average, mu, of whatever probability distribution is generating this data is between 79.9 and 80.4%. So we can see that we've nailed down the value of mu for this distribution really quite well. Now, let me show you a shortcut. Obviously, since business analytics practitioners do this every single day, inference on averages, we're not really going to worry too much about actually typing all of this out just by hand. There's a name for this procedure, kind of coming up with the confidence interval for an average, and that is the t.test command. That's kind of our procedure. What we do is we just say, hey, let's run t-test on ex2.census $response rate, and this is going to make the confidence interval automatically for us. So what it reports back to us is the average value of our data, that 80.2%, and bam, we have that confidence interval. There's that degree of freedom parameter associated with that t-distribution. The only thing that it doesn't give us is the value of that standard error. So we either still have to calculate it just by hand, or actually that's kind of just what we need to do. It'd be very difficult to get it otherwise here. So t.test will very quickly get you that 95% confidence interval. What if you wanted a different level of confidence? Conf.level equals 0.99 for 99% confidence. So running t-test is really quite straightforward. That's great. And so there's a slide or two about using that t-test command in the notes as well. So there are a few more examples in the notes. There's another data set that's built into Reg class, the ex7.catalog, that's talking about catalog purchases. And so you can review inferring the average number of days, essentially it's been since customers have last purchased with that catalog, getting the average, the standard deviation, the standard error by hand, getting that 95% confidence interval, and then also running t-test with to get that answer, kind of the easy way out. Got the t-test for the bike demands, which we just did, and the interpretation with the average, standard deviation, standard error, etc. T-test for the census response rates. We're all good to go. So I think the last example that I want to leave you with, because this brings up actually a really important point, is when to actually analyze the average and when to maybe analyze something a little bit different if you want to be summarizing the typical value you see from a probability distribution. Now, in business analytics, we've seen time and time again that most of the data distributions we observe are highly skewed. That's why that log normal distribution was so useful, because it has that built-in skew to it. The Weibull distribution, exponential distribution, these are all distributions that give us a fair amount of skew. And so let me look up the donor data set in Reg class. And specifically, I'm going to look at a column here called the median home value. This data set is recording whether or not previous donors to a veterans charity gave in a particular year, and if so, how much. And some of the demographic information we have on these donors is the median home value in the neighborhoods that they're living in. Not specific home values of the donors themselves, but just, the median value in that neighborhood here. Now, because it's business analytics, of course, if we look at a histogram of the data values, what we find is a pretty skewed distribution. Now, how many data points do we have here? Well, a ton, 19,000. We can make a confidence interval for the average value of this distribution without any sort of complications. We're meeting this large enough sample size condition, so coming up with a 95% confidence interval is trivial. T-test X, we're 95% confidence that the average median home value among the individuals that donate to this charity is somewhere between 1,066 and 1,093 here. Now that doesn't seem right, so let me make sure that I got that. Maybe this is, I think the units are in something else here. Obviously, I want to go live where these people are living. If they're paying $1,000 for their house, that'd be great. So this must be coded in some other units here. But the point will still be the same behind this analysis. We need to ask ourselves, well, should we actually be doing an inference on the average itself? Let me add a line here on the plot. Let me AB line it. V equals the average value of X. I'm going to make it thick, and I'm going to make this red. So because we have a fairly skewed distribution, the outliers, these large values very far away from the peak, are kind of dragging the value of the average up towards it. And so if you look at this histogram, you might say, I don't know, is that red line, this average here, doing the best job it really can at summarizing the typical value? Well, it's a matter of personal opinion. What would happen if instead we looked at a histogram of the logs of these values? Well, if we look at the histogram of the logs, this is a bit more symmetric than the distribution of the original data values we were looking at. And so what if we did the following? What if we said, all right, well, let's actually come up with some inference about the average value of the logs of these median home values, the logs of the originally collected values. There's some PDF, we can still assume that's generating these data values here. What if we want mu for this PDF, and then we can just untransform it back to the original scale here? What if we do that? If we take the average value of the logs, well, we get a value of minus infinity. So what happened here? Probably jumped ahead. Let's look at a summary. And we have a whole bunch of zeros here. So log of zeros, technically not defined. That's that minus infinity. That's what's confusing R in this case. And I should have done this check ahead of time. We shouldn't have dived right into this analysis before being a little bit more careful. The zeros represent cases where we didn't actually have those data values. There's no place where there's free housing. So why don't we just get the values of X that are positive here? So these are all the values that are positive. Looking at the histogram, we still have that skewness and everything. Let's actually make more breaks here. Let's go up in increments of 100. So here you can see that distribution a little bit better. Still have 19,000 data points, so this 95% confidence interval is pretty legit. All right, but should we be using the average here really to summarize the typical value from this distribution? That's kind of far away from the peak. And if you're like me, I kind of like estimating something, a typical value, from where distribution peaks. So what if we wanted to do that? Well, let's make a histogram of those logs once again, a little bit skewed. If we get the average value, well, that's right at around 2.93 or so. So if we were to unlog that value, basically take 10 and raise it to that power, we get a value of about 842. All right, let's go back and remake this histogram here. What if I make a vertical line at this quantity instead? I'm going to make it blue. Quite a bit closer to the peak. Not matching up exactly, but this is why I very often like to actually do my analysis on the logs of the original values instead of the original values themselves, because if I go and unlog the results, I feel like very often I end up summarizing the distribution a little bit better. Now, there's a wealth of statisticians out there that's going to disagree with me on, whether or not this is a legitimate procedure to really do. But for me, I feel like we get a better impression of what a typical value is by actually analyzing the logs of the original values when we're dealing with a very skewed distribution, and then just unlogging those results. So what do I mean by that? Well, here we have come up with a 95% confidence interval for mu, but we've kind of argued that mu, this red line here, might not be the best summary of a typical value. So instead, what I could do is I could run t-test on the logs of the original values to get a 95% confidence interval for mu of the log of the values, whatever PDF is responsible for making this distribution right here. And so I have a lower endpoint, I have an upper endpoint. If I take 10 and raise it to these vector of powers, I would instead get a 95% confidence interval. Not now for mu anymore, because this is for something a little bit different, kind of the untransformed values of the logged values. But I get a 95% confidence interval for what I'll call the typical value of between 834 and 850. Quite a bit different than this 1078 to 1105. And I feel like, if we go back and revisit this histogram, let's zoom in a little bit from 0 to 1500. If we did the confidence interval on mu, well, we're kind of landing in this 1078 to 1100. We're kind of in these two bars right over here as our best guess, our best summary of what mu is for the data generating distribution. If we look at the logs, do the analysis on the logs, then unlog it, we're around the 800s. That's right at around here, a little bit closer to the peak, which I feel like summarizes the typical value a little bit more. So upshot is that if we're dealing with a very skewed distribution and we want to just be summarizing the typical value that we might see from whatever PDF is generating these values, mu may not be in our best interest to focus in on. I kind of like getting closer to the peak, and so to get us closer to the peak, instead we'll do the analysis on the logs of the collected data values, get our average of the logs, unlog it to get a better idea of what the typical value is, get the confidence interval for the mu of the logged values, unlog it to get a confidence interval for the typical value from that distribution here. So my kind of little special twist on doing this sort of procedure for business analytics. You won't learn that in a statistics class. In fact, a lot of statisticians would be kind of horrified at my suggestion, but I think it works pretty well. If you like getting closer to the peak, that's a good way of going about it. So that's conclude what we have for Unit 11 for now. The next video is going to talk about how we actually compare averages between two groups, doing some sort of A/B testing. And this is really the bread and butter of analytics. We talked about this with the census response rates. Which county is better? Is it Knox County, or is it Hamilton County, or is it Shelby County? We want to compare the average response rates between groups here. How do we do that? How do we come up with some statistical conclusions here? Much like when we were comparing probabilities. And how do we do that across multiple groups? So see you then.